Morning, everyone. There we go. That's good. All right, so welcome to the lecture. So I just randomly searched for a cartoon quickly on the internet, but this kind of came out of a discussion yesterday that I had with a student after the lecture about AI ethics. And the question was sort of, well, what about, robot rights? And this is kind of the extreme joke of it. When the robot revolution came, did you say thank you to the AI, or will they kill you? But a funny thing is, I always say please when I work with an LLM. Why? Because they were trained on human speech. They were trained on what humans write. So if I would say please to a human, I should say please to the LLM because it'll give me the response I want. More likely anyway, because it's been sort of programmed on that sort of thing. However, the AI companies get very upset when you put things like please and thank you in because it costs them money to respond to it. But so it's an interesting kind of philosophical question about, should we actually be thanking an LLM? Should we be saying please? The AI companies don't want us to, but I do it because I think it'll give me a better result. So anyway, just back to that whole ethics thing. So I thought that would be a fun way to start the lecture. Secondly, I have actually figured out how to record lectures with audio. So the ones that do have audio, I am trying to post, so they are there. Yesterday's one at least worked. Today's one seems to be working. So hopefully that will continue.
Being nice costs them money.
Being nice to an LLM costs them money.
I'll be very nice to them.
Yeah, so everybody's going to be very nice to them. You don't have to, they're losing money already. Also just want to say the provisional schedule has an update. So I had someone ask me when is the first prac due? Well, the answer is 24th at the moment. As always, if there's a reason why we need to postpone it, please let me know. It is before the pre-prac lecture for the simple reason that if we make it after the pre-prac lecture, no one comes to the pre-prac lecture, and then we have bigger problems for the next prac. So that's why it's done like that. But if there is a problem, please let me know. There, yeah, okay. Yeah, that's been there for a few days. All right. The thing I want to draw your attention to is on the 25th of March, we will have a guest lecture. It's a guy I know who works in cybersecurity, got a PhD in cybersecurity, among other things, and he's going to come and speak about applications of AI to cybersecurity. One of the interesting problems that generative AI brings in is you can actually use it to hack systems. Isn't that a nice thought? Yet another way for people to steal your data. But anyway, that's a guest lecture. As I say, roll call will be taken. I'll give more info closer to the time. I've asked 3 people to come and chat to us. I might actually ask another person. Strange enough, one of the people I asked about the content of this course, the person's response was, the course content looks fine. Most of the really advanced stuff is only used in research labs. But you need more real-world sort of applications like, wouldn't you like to come and tell us about real-world applications in that case? So we will have some guest lectures during the semester. At the moment, there's one scheduled for 25 March. Hopefully there will be more. All right. Anything from your side at this stage? Okay, that's a relief at least. Sorry, I'm really paranoid about this recording thing now. All right. Okay, so yesterday we started speaking about agents, how we can define them, what a percept is, what an action is, what an actuator is, the difference between an agent function and an agent program, the one's internal, the other one's external, performance measures, and we then spoke about what a rational agent is with that thing I quoted more than once. What we're going to just have a quick look at now, to start with, are a couple of considerations that we need to bear in mind when dealing with agents and when dealing with what is rational. And the first one is, if I get a decent pen, come on, let's go, I like orange, omniscience. So that's a big word which just means knowledge of everything. So it's all-knowing. It's normally applied in the sense of God. God is omniscient because God knows everything. And the issue here is that we can't build an agent that has knowledge of future events. At least not with our current understanding of the universe. So we can't expect our agent to respond to future events before they've happened. We can't expect an agent to have knowledge of things we haven't given it in its percept or percept sequence. So we need to be realistic about what an agent can achieve. Even if we have a perfect agent, we're still limited by what we can feed into it. So we need to have our expectations being realistic. And I think at least some of the criticism of LLMs is just, you're not being realistic about what is achievable. A lot of it is just, come on, somebody didn't think of this, like counting the R's in strawberry, but different discussion. But a lot of the time, just assuming that the thing is omniscient is unreasonable, yet we're inclined to do it. We're inclined to look at it and say, but it didn't know that, I don't know, whatever was going to happen, that Trump was going to invade Venezuela, so therefore it took the wrong action, useless machine. No, nobody knew it was going to happen, except the person who placed a massive bet on it happening the day before. But that's a different discussion. Okay. So we need to be very careful about that. Yes, sir?
So you should train an LLM on poly markets. That will predict.
Poly markets? Oh, yes. Yeah, where basically you get people to bid on the likelihood of events. And that turns out to be a better predictor of what's going to happen than most predictions, strangely enough. Well, the thing is, if I said to you, would you be prepared to put money on the United States invading Iran this year? Would you be prepared to bet on it? Yeah, sort of consider. Would you be prepared to put money on the United States invading China this year? No. And by sort of polling people in that way and saying, would you put money on this, you actually get surprisingly good results. Which is weird, but there you have it. So, omniscience is our first thing we need to consider. The second thing is information gathering. Information gathering. So here we're dealing with, remember, our agent's action is determined by the information it's gained through its percepts and its pre-existing knowledge. So in this case, there are times when the rational action is to do something that's not leading to the best expected result, but that allows us to build up more information, to learn more, rather than go head first for the best result. So we need to keep in mind that rational action often entails searching in order to gather more information, not to get closer to the better solution. In fact, there is at least some point in the textbook where it says, given a choice between moving towards the best solution or moving in a direction you've never gone before, 100% pick the direction you've never gone before. So in that case, and I can't remember the exact assumptions behind it. Be very careful about statements like that because there's a bunch of disclaimers that come with it. But in that case, the rational action is not to move towards the goal, it's to move in such a way as to explore. So we need to keep that in mind when looking at agent behavior. Just because it didn't move closer to the goal doesn't mean it's not rational. All right. The other thing is learning, and it gradually learns things like the rules of the game. So the best chess engine in the world that is kind of still available is, Stockfish. Is Stockfish, and you can go and download it right now. It's an open source tool. However, it was apparently creamed by the alpha chess thing that Google developed, which is not available. But what that thing does, the alpha chess thing, is it starts off with just no information about the game and gradually figures the rules and everything out as it's going. So in that case, the agent needs to learn the rules of the game. So we need to give it time to accomplish that learning. We can't just say, well, it should know the rules of the game by now and it doesn't. Useless machine. We need to take into account that learning can take time, as you guys are busy discovering sitting in this lecture. So we need to realize that all agents, provably intelligent ones, I mustn't point at myself on that, provably intelligent ones and artificially intelligent ones need time to learn. So that's important. We also have autonomy as another consideration. So how much do we want the thing, is that right? Yes. How much do we want the thing to act on its own, and how much do we want to have control of it? Now, the hassle here is the best performance an AI agent that cannot learn has is the day it's released. Because at that stage, the training is just finished and you let it go. After that, things continue changing in the universe. You actually need to update the agent to keep up with the changes in the universe. But how much are you willing to let the thing figure stuff out for itself? At what point does it decide that humanity is the enemy and needs to be destroyed? as a really ridiculously extreme example. So one needs to ask and say, well, how much do we trust the thing in order to do what it should do? And then we have a task environment. This is where the task is executed. Task environment. So this is where the problem needs to be solved. It's where the agent works. And that can place limitations on the agent. We'll see examples of this during the course of the semester. And in a sense, a task environment is the problem, and the agent is the solution. But it's obviously limited by the scope of the problem, the permission we give it. A simple example is a software agent only exists in cyberspace. It doesn't deal with the real world. It only exists in that man-made domain of cyberspace. But, as I said earlier, we could now have software agents hacking your computer in previously unseen ways. So this is kind of interesting. So these are things we need to keep we need to take account of when dealing with agents. All right, then the textbook also mentions a couple of things we need to consider about an agent, and these are quite important because they place strong limitations on it. I should also just add, a lot of these considerations in this chapter are valid to anything, not just in the context of artificial intelligence. So that's why some of the comments I've made have been about, in finally a project, remember this, because a lot of these considerations are valid in any context. And this is a nice example of that. So we have the performance, the environment, the actuators, and the sensors. Why in this order? Because it spells peas. Okay. So yeah. So what this is these are the kinds of things that we need to consider when working with agents. And again, not just intelligent agents. So what is the performance we desire from the thing? What do we actually want it to do? And again, we want to specify what the agent has to do, not how it has to do it. Give it the freedom to explore interesting possibilities. The environment obviously places restrictions on what an agent can and cannot do. The environment can also kill an agent. It can be, later on we'll deal with the concept of safely explorable environments versus not safely explorable environments. So the environment can have very strong influence on an agent, the way it works and what it can do. As I've already discussed in connection with that diagram we had yesterday, the actuators and the sensors very strongly determine what an agent can and cannot do. If you can't measure something, you need to somehow infer it. You need to build a model of that thing that you can somehow get some way of reacting or some estimate of that value in order to make use of it. And if you can't do that, well, then you can't act surprised if the thing doesn't react to that information. Again, that whole thing about we can't assume our agents are omniscient. All right, we can't assume they have knowledge about things that we don't give them. So this is another way of looking at it. There's some examples in the textbook where they go through an agent to do this. What is the performance we desire? What is the environment? What are the sensors? What are the actuators? It's actually quite a nice framework for thinking about things like this. Right, now we come to the fun stuff. Well, I'm a lecturer. How much fun can it be? Okay. So these are things that are fairly important, and what we're going to see, especially in the first part of the work, but throughout the semester, is as we change the assumptions around these issues we're going to look at now, we completely change the agent that we want in that environment. There are certain assumptions that mean that we can apply a certain approach, but if one of those assumptions is loosened or completely broken, we have to apply a completely different approach. So these are actually quite important issues from that perspective. So let's start off with observability. I need an S. Observability. So we can have a problem that is partially observable, fully observable, or unobservable. So this is how much can we just directly measure, how much can we get out of the percepts, and how much does the agent need to infer? And incredibly enough, there are cases where we have an unobservable environment But we can still have a solution. And we can still build an agent that will find us useful solutions in that context. There are lots of additional constraints and lots of additional complexity that comes as a result of it. So we'd rather have a fully observable. Everything we want, we can observe, we can react to that. But it's not always the case. And there are actually some nice examples that come up later that have to do with this. So what can we see about the environment? What information can we get from the environment, including potentially nothing? All right, then the single versus multiple agents. Single versus multiple agents. Now let's not speak about that at this stage. So if it's a single agent problem, then the agent can act on its own without regard for what anybody else thinks. However, if there are multiple agents, we now have a number of interesting possibilities that arise. We can have a zero-sum game. My gain is your loss and vice versa. We can have collaboration, we can have competition, different levels, we can have shifting allegiances, but the way one interacts with different agents in an environment changes the way we have to approach the problem. And we'll see this when we start looking at game-playing agents later on, and things like the alpha-beta search. Because how do you then work in an environment where there's another agent that is trying to maximize its performance metric, it's also a rational agent, while our agent is trying to do the same, or potentially multiple agents in the same situation. Very, very different to a single agent problem where an agent just has to solve its problem. An example of this, some years ago I heard, I mean it's fairly common nowadays, you ask Google or Waze or whatever, tell me what the fastest route from home to work is this morning, and it tells you. However, what they found at a point was they were giving everybody the same answer. And the software agent was actually causing traffic jams. So they then had to change the way the system operated in order to account for the fact that they were sending lots and lots of people into the same thing. So they can't treat it as a single agent problem. You can't treat it as each car, there's only one car on the road. You now have to treat it as they're a bunch of cars and they all need to work together to give the best possible solution. So that's a nice example of a single versus multiple agent problem where there were real world consequences, which I still find amazing. The one that follows is very important, deterministic, because it is very different to the previous one, stochastic. So what do I mean by this? Now, this one has to do with whether there are multiple agents in the environment. Okay? This one has to do with, can we predict what the future state of an environment will be with any certainty? Okay? If we can say, I know what my actions are, I can predict whatever other agents are going to do, and based on that I can predict the future state of the environment perfectly. Game of chess is a good example. Then the environment is deterministic. However, if there is some random aspect, like a car driving thing with puddles of water on the road, if you slam on brakes in the middle of a puddle of water, you're not going to stop as fast as you will if you slam on brakes when there's no puddle of water. So there are differences in the environment that even knowing where you are, knowing what your action is, you can't fully predict what the outcome will be. That is then a stochastic environment. Now, please note, whether an environment is deterministic or stochastic has absolutely nothing to do with whether there are multiple agents or not. I've asked test questions based on this a few times over the years, and every single time someone tells me a stochastic environment is where you have multiple agents because you can't predict what they're going to do. No, that is not a stochastic environment. That is a multi-agent environment. A stochastic environment is where you can't fully predict what's going to happen in the future. So there's some uncertainty, some randomness inherent in the environment that has, I'm going to say it again, nothing to do with whether there are multiple agents or not. So we consider these as two totally different things, and the considerations that come out are different. So there are variations of searches that we can use for a deterministic case. We need to use a different version for a stochastic case. There's a completely different type of search, again, that has nothing to do with those when we're dealing with multiple agents versus single agents. So please don't confuse those two. This one has to do with the environment, regardless of whether they're multiple agents or not. This one has to do with whether they're multiple agents or not, regardless of the environment. Yes, sir?
If you were to have multiple agents where one is a rational agent and let's say another one isn't, so it doesn't...
That's still, so regardless of whether the agents are rational or not, it's still a multi-agent environment.
Because, so you have this thing like game theory,
Yes.
where you predict your opponent's move or
Yes.
based on assuming that that
Yeah.
opponent is rational.
But game theory deals with multiple agents.
Yes.
It doesn't deal with stochastic environments. Even then, it's two different cases. Where we're dealing with the responses of different agents and how they interact, that's a multiple agent problem. Where we're dealing with an environment that we can't predict what's going to happen, that's a completely different type of problem. We'll see examples as we go along through the semesters. Hopefully this will become clearer. But just bear in mind, this one has to do with the characteristics of the environment. This one has to do with the number of agents. And they are separate. All right. Thank you. Yes, sir?
I just want to make sure, Rob. So the domestic versus stochastic, it's just environment, it's not from an agent's perspective. So an agent it can seem like it's a stochastic environment from the agent's perspective.
No, this is as seen by the agent. So one of the things that leads to a stochastic environment is if you don't have full information. So we can't predict the weather tomorrow with any certainty because we don't have absolutely perfect information of every molecule of air on the planet all the time. If we did, we could probably predict the weather tomorrow with quite a bit of certainty. But because we don't have that full information, to us as agents in this environment, there is uncertainty. So this is very much from the agent's perspective. Good question, thank you. Actually, both of them are good questions. Keep them coming. Also, as I said to someone who came to me after the lecture yesterday, if you've got a question and you're not sure whether you should ask it, rather err on the side of asking it. For two reasons. Firstly, there's a good chance someone else has exactly the same question, is also thinking, should I ask this question? The other thing, which I've seen happen multiple times, is you might be asking a question that someone didn't even realize was a question. So rather ask. I appreciate the questions, and it's much easier for all of us if you ask me questions. So thanks very much to the folks who have. All right, anyway, back to this. Then, the next big issue is episodic. Whoa, let's go back to the right pen. Episodic versus sequential. Yeah, sequential. Okay, so the difference here is, do previous actions affect what happens now? So, for example, there's a data set that someone set up from scans of handwritten digits from letters, letters sent in the mail. Because someone wanted to make a system that could scan a letter and figure out what the postal code is so you can route it. Okay, that is a lovely example of an episodic case. A letter comes in, you scan the number, you send it off. It's done. That doesn't affect what happens next. The next letter comes in, you do the same thing. You send it off. It's done. It doesn't affect what happens next. So that's a nice example of an episodic case. A sequential case is something more like a game of chess. Your first move affects the result of the game throughout. Yes, the effect will gradually diminish, but everything you do contributes towards the whole. And again, the way we approach the problem differs dramatically depending on whether each episode happens in isolation or whether they gradually build up over time. I hope that makes sense. As always, if it doesn't, wave at me. Then we have static and dynamic environments. Static versus dynamic. And this is the environment static until the agent or agents do something? Or does the environment change continuously without the interaction of the agents? Okay, so static is a game of chess. Nothing happens until one of the players makes a move. Although, the moment you add a clock, so you have a timed game of chess, now it becomes semi-dynamic. Okay, why do they call it semi-dynamic? Because the chessboard position doesn't change. It's not like, in an army where you're fighting a war. The general sits back and says, I'm going to go and sleep for an hour. The world doesn't wait for him to wake up before something happens. It just keeps happening. In chess, that doesn't happen. But while the agent is thinking, the time is running down. So something is changing. Okay, so chess on its own is a static environment because nothing changes until the agent takes an action. With a clock, it's sort of a bit of both. And a dynamic environment is much more like a real-world situation where things are happening. When you go to sleep at night, you wake up in the morning, stuff has happened, stuff has changed. So the real world tends to be more dynamic than it does static, but there are problems where we can kind of shoehorn it in and say, you are going to be a static problem and we're going to solve you as such. This is not the same as stochastic and dynamic, okay, stochastic and deterministic. This has to do with how much certainty and uncertainty we have in predicting the future. This one has to do with, does the environment change while the agent is making a decision? All right. And again, this and this are different things. Just because another agent has done something and caused an effect on the environment does not make it a dynamic environment. That makes it a multi-agent environment. Dynamic is when the environment itself changes. Okay, so an example of that would be Test cricket. You play for 5 days. The pitch you play on day 1 and the pitch you play on day 5 do not look the same. And the way you approach the game on day 1 and the way you approach the game on day 5 change because of the environment that has changed. It's got nothing to do with what either team has done. It's just got to do with the environment is changing. Yes, sir?
Well, how could a dynamic environment be deterministic?
Because as long as you can predict exactly what's happening. So the clock running down on a chess thing, that's the dynamic nature of the environment. But you can perfectly predict how it's going to run down. So it's, yeah, it can be dynamic and deterministic. These questions are hard because I now have to try to dream up an example for this. So good questions, keep them coming. You're making me work for my pay. All right. Yes?
So would you say that for something to be deterministic, it needs to be modeled by some math?
Either by some math or some form of model. Okay, you can potentially get models that are not mathematical, which I know sounds like I'm lying and I can't think of an example of a model that isn't mathematical. But it's just as long as you've got some way of doing it. So, I don't know, what would be an example? So, someone modeled the Dutch dike system, not using a computer, but by building a scale model. That's a model that's not a mathematical model, but it very accurately predicts what is going to happen. So it's really just saying we've got some way of predicting what's going to happen in the future and how much uncertainty is about it. So if the future is, we can predict absolutely what's going to happen in some way, then it's a deterministic environment. If there's uncertainty, then it starts becoming stochastic. Right. So these are characteristics of the environment, not of the agent itself. These are things that the environment imposes on the agent, and the agent has to respond to the effects of these various characteristics. All right, then we can even go for, in the extreme, known versus unknown. So, how much information do we give the agent to start with? Or do we just say, right, here you go, you're in an environment, make something happen. So we can even go that far. And that's got to do with how much knowledge is available a priori. Now, a lot of this seems a little bit theoretical at this stage. Hopefully, as we work through the semester and see examples of it, you'll start seeing what the effect of loosening each of these constraints is. All right. Any more questions there? I used to ask, is everybody happy? No questions. Any questions? I sometimes get a question. All right, so, and again, this is the kind of thing that is also very useful outside just the narrow confines of this course, because a lot of these questions do affect how you have to build any system, for example. All right, now, we've already spoken about the agent program and the agent function. So the agent program is the internal thing, that's not an M, that's an M, is the internal thing in the agent. It's what the agent implements in order to achieve its function, which is the function is the thing we see when we look from outside. Spoke about that yesterday. So we've got these two ways of looking at it. Now, What we're going to then say is that we've got an agent architecture. Okay, architecture. So now we have an agent architecture as well. And this is the system implementing the agent. So this includes things like the computing platform using, the sensors, the actuators. So this is kind of what the agent is doing, either looking at it from the perspective of inside the agent or looking at it from outside or what we want. This is then what we use to implement the agent. So the sort of the physical manifestation of the agent, if you will. And the agent itself is a combination of the architecture, because the way we implement it does make a difference, plus the agent program. So this is how we represent the thing internally. So very important to bear in mind that the way we've implemented the agent, and I've already said this in various shapes and forms, it's just another way of looking at it, is that the way we implement it has a massive effect. So a lot of the time, a lot of AI researchers find the biggest, hairiest computer you have, throw it at a problem, and oh, look, result. That's normally not practical for most engineering problems because you have SWAP, C, size, weight, power, and cost, problems that you need to overcome. So you can't have the biggest, hairiest computer you want because maybe it needs to fly on a drone. That's a problem that people talking to me have spoken about recently. So we need to take into account both how we're going to realize the intelligence, so that the program we're going to use inside the thing, and the implementation of that program. Neither of these exist in isolation. So something I thought of many years ago now, the difference between electrical, electronic, and computer engineering. And I finally finished it. I thought of the first two when I was a student. The last one I thought about a year ago. So electrical engineering, if you touch it, and it kills you, it's electrical engineering. All right. If you touch it and you kill it, it's electronic engineering. And if you can't touch it, it's computer engineering. All right, so you need to consider the electronic and electrical engineering as part of your agent, not just the computer engineering aspect. It's kind of what this boils down to. Yeah, not going to worry about that. Now, let's have a look at some diagrams. Didn't expect that reaction. All right, so go there. Thank you. So the first one we're going to deal with is a simple reflex agent. So we have the sensors which get the percept in. We then, on that, have some estimate of what the universe looks like now. These are in the textbook, so you don't have to take photos of them, I promise. So it then evaluates what the world is like now based on its percepts. And then it simply says, I've got rules, whatever they may be. Could be a neural network, could be a fuzzy logic system, could be an expert system, whatever. We've got some sort of rule which then determines the action, and we take the action. Great. So here you can now start seeing the effect of our different consideration of environments. This type of thing is brilliant for an episodic environment. So in other words, you do something and then it goes away and you have to do it again. Your previous actions do not affect the future results and the future problems. So this is where a reflex agent, or simple reflex agent, is good. So if our sensors give us the full information about everything, then we have everything we need in order to make the decision that the rational decision that we need to implement our rational agent. If there is some nature of sequential thing, we can still use a single reflex agent, but then we'd better have every single thing over the entire history that affects this decision included in there. So the point is, this is probably the simplest architecture that one can have, but as you can see, it's quite limiting. Because you can't go and say, build towards a better result in future. Because there's no notion of try to predict what's going to happen and make that better than it is now, or try to take actions that will lead me to a better result eventually, but not necessarily in the short term. So it is quite limited, but it can work nicely. The other problem that we have with something like this is every time the percept is the same, this agent will take the same action. So in a mapping type problem, If you go round in a circle and end up back where you started, you're going to go round in the same circle again. And you're going to keep doing that ad infinitum, which is not desirable. So sometimes what we could do is just add a little bit of randomness in there. So in other words, if we end up back where we started, there's at least some chance we're now going to go a different route and not just keep doing the same thing over and over again. So very simple, surprisingly useful, actually. Just want to check I haven't missed something. Okay, great. The problem with this is, as I say, you can't build up to something better in the future. So then we move to a model-based reflex agent. And the big difference here is we've got our percepts like we had before, but now we have this state, okay? Information about how the world evolves and information about the actions and how they will affect it. So now we can start seeing the difference that a deterministic versus a stochastic environment would have on the operation of our agent. In a deterministic environment, these things can be perfect because we know exactly what is going to happen in future if we do a certain thing. So we can absolutely, perfectly predict what the world is like now because there's no uncertainty. In a stochastic environment, this what the world is like now has some uncertainty to it. So we can see how that assumption about the environment affects the agent. What's the difference here? The difference here is that we can build a better estimate to the environmental state. So remember, I spoke about how if you don't have information in your percept, you need to infer it in some way. Well, this is one way that you can do that. You can have a model of the system internally that says, okay, I can't measure the temperature of the molten iron in the middle of one of those big crucibles that they use, because any sensor you try to put there is just going to melt. However, if I can have measurements at other points, I can build a model that will allow me to infer what the temperature at the center will be. So that's the goal here, is we're trying to get more information than our percept gives us. We're trying to have a deeper understanding of the environment than our percept gives us. Prof. Craig and Prof. LaRue do a lot of work on model-based control. And it's, again, this kind of idea of we can't actually measure everything, but we do want to control everything, so we include a model. Okay. How we create that model, that's a discussion for future this course. The bottom bit down here is exactly the same. Once we have our understanding of what the world is like, we just take an action again. So again, it is more difficult in a case like this to build something that is going to build towards a better result. However, included in this state, which includes the effective agent actions, this estimate of what the world is like now can include information that will encourage certain actions that will lead to long-term goals being achieved. So we can now have a system where it's not just dependent on the current percept values. It's dependent on the current percept value for sure, but it's also dependent on our model's value, and that model value can include a history in it. So we're now getting away from that problem that we can only have what we can measure right now affecting our actions. So that's the goal of including a model. And this could be a mathematical model, it could be an AI model, it could be whatever. The point is just there is a model. All right, let me just make sure I've got everything here. I love this. First comment. A model-based agent uses a model. Wow, who would have thought? All right. I've said that. Okay, great. Then, we're now going to make it even more complex. And we're going to go to this one. And now we've got a goal-based agent. Model-based, goal-based agent. Now the difference here is that we've added this little block here. Now you can see that what is explicitly included here is not only our model of the environment, but also some estimation of what will happen if we take particular actions. So now we can start saying, well, I want to achieve a specific goal, okay, in the long term. That doesn't mean my next action has to greedily try to get me there. That traffic problem, if the shortest route is congested, it might be better to go in a longer route because it'll actually be quicker. So by having goals rather than just what we had in the previous stuff, we can now go and build towards a particular objective without having to take only good steps, or only steps that look good. The other thing here is that an agent like this, we can change its behavior just by changing the goals. Okay, so I can create a lovely mapping algorithm that tells me what the fastest route from my home to work is. But you can't use it. I can't use it to go from work to home. However, if we change the goal to, we're going to set this agent up to go from a point to another point with the shortest distance. By changing the goal, we can now completely change the functioning of the agent without changing the vast majority of what is inside the agent. So having a goal is a really good way of doing this. So it's a way of making our agents more useful. So it's not just you can only use it for this. It's we can change the goal and say, well, I want it. We could even go and say, I want the shortest distance, or I want the fastest, or hey, I've got a helicopter. What's the shortest distance for me now? Potentially by just changing the goals, well, okay, the helicopter's a bad example, but by changing the goals, we can reuse agents, and that's the primary benefit of having a goal-based agent. So you can see how we're gradually making the agent more capable, but at the same time, we're making it a lot more complicated. We're adding a whole bunch more stuff into it. But wait, there is more. All right, and now we can get to this sucker, which is a model-based, utility-based agent. So now you will notice our goal is gone. And now we have a utility. So we've again got our model, which is based on our percept. We've also got our goals. So we've got that estimation, that model, that prediction of the future, if we take certain actions. Now we have over here, if we were in that state, how happy would we be? Okay, what would the utility be? Utility is happiness, whatever. It's some measure of goodness. Okay, so how good would that solution be from the perception of the agent? Now what's really useful in this is it allows conflicting goals to be played off against each other. Because in our utility over here, in this how happy would I be in such a state, we can trade off conflicting requirements against each other. So you guys want to be at home sleeping now, not sitting here listening to me. But you would also like to pass this course. So my attempt to maximize the utility is to tell jokes. Bad ones, I know, but I do try to tell jokes. So it's a way of trying to make, we have to achieve these conflicting goals. Let's try to find a way of trading off between them. Utility is a very powerful way of doing that. It's also useful if it's impossible to achieve a goal, all right? Because we can still say to the agent, yes, you can't necessarily achieve the goal, but how close can you get? And that then becomes a utility, a measure of goodness, rather than have you reached the goal or haven't you? All right. And again, the way you approach the problem is very difficult. It's very different in these two cases. So this is kind of the most general that we can have there, but it is a lot more tricky to set up, because now we need a model, we need to predict what happens in the future, we need a whole utility analysis, and we need to include this system as well. So it's a lot more complicated, but it's got a lot more capability. And this is what I was saying about earlier, where you have to take the architecture and the program into account. Remember, this is the program of the agent. It's how it internalizes its function, what it has to do. This program has a lot more requirements than the simple reflex agent. Okay. Is that extra complexity always justified? No. Is it justified in some cases? Yes. What will it depend on? Well, things like what the problem actually is and what the architecture is. Well, how are we implementing the system? So keep in mind that that is a fairly big deal. The other thing to bear in mind here is this agent is not going to optimize for any external performance metric. It's going to optimize its utility. So if you mess up that utility computation, you kill off humanity. Okay, that's extreme, but the point is you need to be very careful about how one specifies that utility, because otherwise you're going to get the wrong behavior. So it's not just you ambiguously reach a goal or you don't. especially a lot of the earlier stuff, there's a goal state, we try to get to the goal state. If we reach it, success. If we don't reach it, failure. Easy. In this kind of case, there's mixtures between success and failure, so quantifying it becomes a lot more difficult. All right. Let's speak about learning agents quickly, and then we'll call it a day. So, then, let's completely change everything. And now let's look at learning agents. Now, a learning agent internally has to have some aspect of the agent that can change over time. So the big benefit of this is this thing is not constrained by what we know when we set the thing up. So it's not constrained about prior knowledge. The thing can learn and improve any aspect of it. So it could be the model, it could be how it responds to the environment, it could be how it determines its utility. Any of these things can be subject to learning. Okay, so learning is not just one aspect. The important issues here are, we do have some sort of external performance standard. So we need to tell it, this solution is better than this solution. All right, and that could be as simple as play two agents off against one another in a game of chess. The one that wins is the better one. There are lots of problems with that. You can win through luck, etc., etc., etc. But that's an example of some sort of external performance metric. We still have our sensors and actuators. The problem here is this performance element is pretty much everything we had in the previous diagrams. Okay, so everything kind of lurks in there. But there is some aspect of it which can learn. All right, so that's the thing that's responsible for making changes. So knowledge from the sensors, the critic, which takes the performance standard and turns it to something the agent can use internally. So all of that input goes into this learning element, including the knowledge that comes out of there, and it then makes updates to our performance element. So that could be our model of the environment, whatever. It gradually makes updates in it in order to try to make the critic happy. Because when the critic's happy, we're doing well with the performance standard. The problem generator is there to try to say, well, let's do things that will allow us to learn. Okay? So not do things that will necessarily get us closer to the objective, but that's a short-term goal. Let's do things that will allow us to learn in the hope that a greater understanding, a better update to our performance element will give us better results. So we've got the learning element responsible for making improvements, performance element which is responsible for selecting actions. So that's the thing we had before. This is the thing responsible for making improvements. This thing makes suggestions about ways that we could learn more, and that's an input over here. So sometimes we don't take what looks like the best solution or the best action. We take an action that will enhance learning. Okay, and obviously you need a balance between those, but that's the idea. And then the critic tells you how good or bad the solution is based on the external performance standard. Okay, so the key point I just want to make here is, and these are actually terms that one sees quite a bit. I've seen the reference to a critic happens a lot in any kind of learning system. So but it's nice to kind of break it up like this, because you can see how the learning is completely separate from the AI system that's just running the thing. All right, and that is important because, for example, a neural network versus its backpropagation algorithm are two very different things. All right. And then the other thing is this performance element can be any element that's learning, or all of them. All right. I have a minute left, so I am going to say thank you very much, and I will see you I'll see you tomorrow. Yes.